The history of humans is also the story of how we extract energy from all available resources. All the most important milestones in history, from the day our ancestors discovered fire control to the first industrial revolution, all without exception are directly or indirectly related to how we use energy. In a very short span of time, in geological terms, we went from using water, wind, coal, petroleum, and even splitting atom nuclei to obtain energy. And this progress lets humanity advance to the next level on the Kardashev Scale.
Hey, Pedro here. This video you are watching was originally in Portuguese, my native language. This is the attempt of our team to translate it to English, and I sincerely hope you enjoy it. Your feedback is extremely important to us. Now, back to the video.
In a nutshell, the Kardashev scale gauges how advanced a civilization is by looking at how much energy it uses. The scale has 3 types of civilization, and type 1, which is our next stop, would require us to use all the energy available on our planet. Currently, we are close to 0.7 on the scale, using only 0.1% of all the energy available on planet Earth. And for some astronomers, among them prominent figures like Carl Sagan, humanity will reach type 1 between 2100 and 2200. But we have to break through a barrier to get there. Increasingly, we see energy resources becoming scarcer, compromising our energy generation and distribution. A solution seems right in front of us, something with unlimited energy for our lifetime: the sun. Solar panels are nothing new, we're all familiar with them, but what if I told you that their use isn't limited to Earth? That they might allow us to use all the available energy from the sun? This idea might even seem like science fiction, but it's a fact. Solar rays hitting Earth are just a fraction of the sun's constant energy output. And all this energy is being released into space and completely wasted while we could be using it to technologically advance humanity. Just for comparison, we would need about 40 million power plants to generate the same amount of energy that the sun emits for free. On the Kardashev scale, a civilization that could harness all available energy from its star would be a Type 2 civilization. And this is what motivated physicist Freeman Dyson to publish his article Search for Artificial Stellar Sources of Infrared Radiation in 1960. Dyson argued that for a civilization to survive, it would need to reach a point where it used all the energy from its host star. And in the article, he also suggests that civilizations would have to build megastructures around their stars that would capture and store all of their energy power. Dyson wrote this article due to his interest in searching for life beyond Earth. He suggested these massive structures could emit infrared radiation, giving signs of extraterrestrial life. No record of these signals has been found to date, but Dyson was responsible for introducing one of the most daring concepts we know today, the Dyson Spheres. A Dyson Sphere would be a megastructure around a star that would use solar panels to capture and store all the energy emitted from the star. And this stored energy could be transferred to one or more planets and used in a useful way for civilization to survive. In this video, I don't just want to explain how a Dyson Sphere works. I want to show the 10 essential steps that a civilization would need to follow to create a Dyson Sphere around the sun. First step, decide the format of this Dyson Sphere. And yes, I know the name is suggestive. Dyson Sphere. So it's kind of obvious that we already have a shape for it, but in fact the idea of having a spherical shell covering the entire sun is tempting and even makes some sense if we want to capture all the energy the sun offers. But some difficulties arise. The stress on the material of a closed spherical shell would simply be too great, and no known material on Earth today could withstand it. Don't forget that we are talking about a structure larger than our planet, and that it would also be vulnerable to collisions with asteroids, comets, and even the pressure of solar winds. And it wouldn't even be gravitationally stable. This means that if an asteroid were to dent a part of it, it would collapse and likely fall towards the sun. To solve this problem, I present to you the best option, also known as the most realistic, the Dyson Swarm. Unlike the Dyson Sphere, which would completely cover the star, the Dyson Swarm would function as several solar panels orbiting the sun, storing the energy that reaches them. The downside is that yes, we would lose a fraction of the available energy, since not all the area would be covered. But on the other hand, this would greatly ease the gravitational problems that a sphere would bring. Second step, properties of the solar panels. If we choose to go ahead with the Dyson Swarm design, now we will need to decide on the shape of the solar panels that we will use. The weight and size of each solar panel are important precisely because they are the characteristics that dictate how much fuel we will need to launch them into space. At the same time, we don't want small panels because it wouldn't be worth the effort, but we also can't have giant panels because we would spend too much energy trying to position them close to the sun. So we would need to find a middle ground, an extremely lightweight material, and the best suggestion would be something similar to the James Webb Space Telescope. The hexagonal shape made from several smaller hexagons aided in the launch because they were able to fold the telescope's mirror like origami and reduce the necessary area inside a rocket, and that is very important. This would even avoid stress on the solar panels, something that a rigid rectangular or circular panel as we know it would suffer greatly. The hexagons were able to take on a slightly concave shape, avoiding tension and achieving a larger coverage area than if we had used something rigid and fixed. Third step, create your first solar panels and launch them with energy already accessible. Okay, to harness energy from the sun, we first need matter and energy, which are available here on Earth. Again, let's use the James Webb Space Telescope as an example, since it uses solar panels to stay operational, using technology we already have. Since this is something we are already familiar with and have even conducted tests on, this phase would not be so complicated. Moreover, we need to choose an orbit that is close enough to the sun to be efficient, but far enough away to not require too much energy or be swallowed by the solar gravitational field. Furthermore, it would also be in our interest to launch these initial panels in a region that was close to the planet Mercury, and I will explain the reason shortly. Fourth step, obtain energy. Interestingly, the problem that started this whole idea was the scarcity of energy, which will now be resolved. As we started placing solar panels in orbit to assemble our Dyson Swarm, we will use the very energy that is being generated by this first batch of panels to continue the project. But here we encounter the first problem, cost effectiveness. With just a few panels in orbit, the energy generation is still very low, much less than what we need to make the project self-sustaining. And worse, we simply do not have enough material on Earth to continue creating solar panels indefinitely. And this necessarily leads us to the next step. The fifth step involves finding material within the solar system. Fortunately for us, the inner solar system probably has enough matter to build our countless solar panels. If we combine Mercury, Venus, Earth, Mars, the Moon, and an asteroid belt, we are probably talking about 11 times 10 to the power of 24 of kilograms of material available. It's a lot, so luckily we were born in the right place in the solar system to solve material problems. However, transporting material from Earth, Mars, the Moon, and the asteroid belt to regions close to the Sun would only result in more energy expenditure, which is exactly what we are trying to avoid. So the solution seems to lie precisely in the first two planets of the solar system. Sixth step, destroy Mercury. Okay, I think you weren't expecting that, but I'll convince you it's the best solution. Mercury is the planet closest to the Sun, and this gives us a huge advantage because it would make it easier to launch panels without spending so much energy, and also with the advantage of being extremely close to our star. Mercury has a relatively low gravitational field, and this characteristic would save us a significant amount of work and energy needed to overcome the planet's gravitational pull. And as a bonus, we will have a planet as our construction site where 50% of its mass can be directly used as material for the construction of more solar panels. It's obvious that after destroying Mercury, we would need to start going to other planets in the solar system to look for material, but a good part of the problem would already be solved here, and it would likely be an amount bringing us close to the self-sustainability I mentioned in the fourth step. Seventh step, automate the entire process directly from Mercury. It would be difficult for humans to reach the planet due to its thin atmosphere and extreme temperatures on the side facing the sun compared to the other. And that's why it would be necessary for machines to automate the entire process, from mining to the construction of the panels, and finally, launching them into orbit around the sun. Being a planet close to the sun, Mercury has the advantage of generating solar energy to power all these machines. But thinking big, we must automate everything, without exception. Eighth step, create an iterative process of construction and launch. After the first 7 steps, the issue now is to make an iterative process. Essentially, the launched solar panels would provide energy for the production and launch of more panels, which would allow us to launch even more panels, and so on, exponentially. One solar panel would provide the energy to create another one. 2 solar panels would generate 2 more, and so on. In a short amount of time, it's possible to achieve a swarm that would cover a large part of the area around the sun. But because they are small, they would not interfere with the sunlight that reaches us. In other words, humanity can continue to survive. 9th step, transfer energy to Earth and the other planets. Having a swarm of a relatively considerable size, it's now time for us to think about transferring energy to Earth and the other planets. After all, there's no point in creating a Dyson swarm if the energy cannot be extracted in some way. And we must not forget that a portion of this energy will continue to be directed towards Mercury, our major construction site. But at this point, we can already start thinking about using some of the energy for humanity itself. But how could we possibly transmit energy through space wirelessly? Literally, how can we transmit energy without wires? The answer involves radiation, clearly. The first method uses microwaves, which is seen as the best way to transmit energy wirelessly. The biggest problem is that nowadays we can only transfer energy over distances of about 140 kilometers. And yet, most of the energy is lost in the process. The best approach would be to create towers that capture and transmit at different points within the solar system until reaching Earth. And of course, we would also have associated losses, and that's why the Dyson Swarm needs to be large enough to compensate for the energy loss. Another approach would be to do something similar to what the Starlink satellites do, which is to transmit from one to another using lasers. But we could spread satellites that communicate using lasers. The problem is that they have an even shorter range than microwaves. They can only transmit energy usefully up to just 1 kilometer away. Probably a station on the moon would be necessary to receive and distribute this energy to planet Earth. The biggest problem so far, it seems, is the challenge of transferring energy, as the two available methods are still quite limited in scope. So, we would need a huge technological breakthrough to achieve this in a way that makes the investment in a Dyson Swarm worthwhile. But if we manage to solve this last part, now it's genuinely time to harness that energy. 10th step. A new era for humanity. Having solved the previous 9 steps, perhaps the most interesting question is what exactly we are going to do with so much energy available. It's really almost unlimited energy if we consider the vast scope of our lifetime. We could do anything. Probably the first areas to feel the difference in energy would be jobs that require computing where the amount of energy available today is a hindrance. Humanity would see computing leap forward with better results, potentially revolutionizing areas of science, from engineering to health. But a civilization that reached this stage of development would probably already have much of its science complete. The technology would probably already be unrecognizable to us. It would be like showing an iPhone to a caveman. Most likely, the majority of the energy would be allocated to space exploration, precisely because fuel to make the ships operate would no longer be a problem. And we wouldn't need to stop here. By improving the technology and our own Dyson Swarm, we would have enough energy for Earth to terraform other planets and create space elevators. But really, it would even be hard to imagine what humanity could do with such a colossal megastructure. The amount of energy is simply beyond our comprehension. But what if you could choose? How would you use all the available energy after building your own Dyson Swarm? Leave your thoughts in the comments. Thank you very much and see you next time.